Continuing with whatever we saw in the previous lectures, we are going to discuss or continue to discuss the hardwired logic design. Earlier we looked at what the firmware approach was, that is a ROM based design. Fine. We have taken in fact master slave flip flop as one simple example for which we are designing these based on these two approaches, that is the hardware approach as well as the firmware approach, just to see how a controller works, that is the whole point. Okay. Instead of considering all the states in a computing system, specifically a processor based system, and then seeing the various states and so on, we are just taking a simple example. So, let us remember that always. Now, the hardwired logic design, in the previous lectures we came up to the point of arriving at the Boolean equations or the Boolean functions for the two state variables. What are they? We found that in the implementation of master slave flip flop there were essentially 4 states, okay, 4 states, and it was accepting in that particular one, it was accepting 3 inputs, that is yj, yc and yk, these were the 3 inputs, and it was generating 2 outputs, namely h0 and h1. Fine. In the process of this accepting these 3 inputs and generating these 2 output, we found that the system goes through 4 states, that is more important. Essentially the user is concerned with these 2 only, that is inputs and outputs. The user is not concerned with anything else. For instance, state the user is not concerned with. It is actually the designer who introduces the states, mainly because having state by state approach he will be able to design the system, that is important. Now, the starting point for this was the Asm chart, the same chart for which based on which we also did our firmware design, right. Now, let us take a look at the chart to recall whatever we had seen so far. So, the particular system has 4 states, and we mark this as small a, small b, small c and small d, and it generates 2 outputs h0 and h1. So, these are further same thing h0 and h1, and the inputs are there in the diamond boxes yj, yc and yk, right. These are the things we discussed this in detail. Now, we found this particular one, this system or this you may call it as a machine. Okay. This machine is in one of 4 states at any instant a, b, c, d, which can be represented using 2 state variables. What are they? Capital A and capital B, right, using 2 state variables. Now, these 2 state variables physically will be represented making use of 2 latches, and what did we do? We considered 2 SR latch. Strictly speaking, it is an S bar R bar latch which we discussed earlier, we may call it loosely as SR latch also, and having reduced let us put it this way, having considered or discussed the behavior of the system which consists essentially of 4 states, we have now reduced our problem to consideration of 2 state variables. Fine. That is, we have a whole machine and then we talk about state by state behavior of the machine, and then subsequently by reducing it to state variables, now we need to consider only how the state variables A and B behave. Agreed? Then subsequently we derive the equations for SA and RA, that is for the state variable A what is the set input, and for the state variable A what is the reset input. Fine. SA and RA we got this equation. Similarly, we also worked out for SB and RB, right. Good. Now, let us go back, and then since we decided that we will be using S bar R bar latch, now we have to derive the equations corresponding to these. that is SA is given as, now we can refer to the chart, SA is given as y c bar and b, fine. So, SA is y c bar and b. From this we get the equation that SA bar, that is we are actually applying the De Morgan's laws, which you would have learned in the switching theory logic design course or so. The inverse of it, the complement of this will be YC or B. What is this? Just to recall, invert this, that is complement this, for which what you have to do is you have to complement each of the variables. So, YC bar complemented will be YC, B complemented will be B bar, and instead of and you will have R. This you get based on De Morgan's laws, right, or De Morgan's rule or whatever you call. Good. Now, this is the one equation we get of SA bar. Similarly, what is RA? RA is given, see the chart, RA is given as Y C bar and B bar, right, Y C bar and B bar. So, Y C bar and B bar. Now, from which we get RA bar as complement is, which is YC, instead of and you have R, instead of B bar you complement it, you get B. So, that is what you have. So, now we have got for the variable state variable A, that is there is one SR latch. You recall it was like this, remember, there is one memory element which will develop our output A. The input for that is SA bar and R A bar, this particular one. Similarly, we have another one for the memory element B. So, we have to work out for that particular one also B, and recall that we have both the outputs A bar, similarly B bar from these memory elements. Now, the input to this what we have is SB bar or B bar. So, we have two latches, that is SA or A latch and SB or B latch, two things which will represent the state variable respectively A and B. Now, the output of these will be A and B, the input for this is what we are working out. So, now we know the output input relationship. Now, let us continue like we did for SA bar and RA bar, we have to do for SB bar and RB bar also. Now, I would straight away work out SB bar after taking a look at the chart. SB is Yj and Yc and A bar, okay. Sj is Yj and Yc and A bar. So, SB bar will be Yj bar or Yc bar or A, that is Yj bar or Yc bar or A, right, or A, okay. Similarly, RB bar would be what is RB? It says Yk and Yc and A. So, RB bar will be Yk bar or Yc bar or A bar. So, Yk bar or Yc bar or A bar. So, now we have these four equations, we have one here SA bar or A bar and we have SB bar or B bar. So, now making use of these two memory elements, let us try and draw the whole circuit diagram, that is the logic circuit diagram, okay. That is, let us take A, SA bar or A bar, and the other one B, maybe okay, B SB bar or B bar. Okay. Actually, we saw that B comes and B bar also comes. This we have discussed earlier. A output and A bar output both are available. Now, how do you proceed implementing this? This, as you can see, is an OR circuit, right. Now, let us assume that we will make use of NAND gates, all right. We will make use of NAND gates and implement the whole thing. Now, you must recall what is known as NAND circuit synthesis. How do you do that? Maybe some of you are familiar. I do not expect all of you to be familiar. So, let us work out the NAND circuit synthesis and then implement this. The NAND circuit synthesis is about synthesizing a logic system using NAND gates. Good. That is, suppose you have got only NAND gates. Now, how would you synthesize the whole logic, right? Now, we know that if A and B happen to be the inputs, the NAND gate output will be A and B the whole bar, right, which again by De Morgan's rule or law is nothing but A bar or B bar. Good. Now, this particular thing must suggest to you something. What is that? Suppose you have only one NAND gate, A bar or B bars, right. Okay. Suppose you have only one NAND gate, then what we find is the output of NAND gate is A bar or B bar, which means basically the NAND gate works like an OR gate with its inputs A and B complemented. In other words, suppose you have one NAND gate with inputs, if you give A bar and the other input B bar, then it means that basically A bar will be complemented, which will be A, and B bar will be complemented, which is B. In other words, as this says NAND gate, okay, NAND gate output shows, it says if you have one NAND gate, the one NAND gate works as an OR gate with its inputs complemented. Good. Now, let us work out further. Take another NAND gate, that is just we are repeating this, let us say, okay, A, B are the two inputs, the output will be A and B bar, that is a usual NAND gate, A and B bar. Now, this particular one you give to another NAND gate, let us assume another NAND gate with two inputs. Okay. What is it actually? Both are same. It is nothing but inverting the whole thing. So, when inverted, the output will be A and B. A and B bar is just inverted there. There is no logic as such here, because the inputs are shorted. It is just inverting it. So, when you invert this, A and B bar becomes A and B. In other words, a NAND gate, okay, which is say from this output level, a NAND gate which is two levels away, this is one level, this is the second level. Okay, with reference to this, this is level 1 and this is level 2. So, which is two levels away, okay, that particular NAND gate works like an AND gate with its inputs true, fine. Now, you know that using AND or AND NOT, you can synthesize all the logic functions that you need. Now, we see that the NAND gate performs as an OR gate or performs as an AND gate, and when the input to the NAND gate is shorted, it just works like a NOT gate. So, a NAND gate itself can perform as an AND or 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 NOT depending on what level it is in. Suppose you want a function, with reference to that see at what level it is it at level 1, level 2, level 3, level 4. Okay. Without much discussion, I can just extend this, the level 1 as an odd level and level 2 as an even level. You can work it out. Any odd level NAND gate, by that what we mean is a NAND gate which is 1 or 3 or 5 steps away from the output, okay, that will work as an OR gate. Now, this is only 1 here. So, this is the odd, this will work as an OR gate. The one which is 2 or 4 or 6 and so on, even levels away, they will all work as an AND gate, but remember the corresponding inputs must be, in the case of AND it must be true, in the case of OR it must be complemented. So, now let us sum this up. We can say that an odd level I have just shown you for 1 level and 2 level, but we can work out and then see about the generalization of odd and even levels. So, an odd level NAND gate, functions as an OR gate, with its inputs complemented. Now, and an even level NAND gate works as an, now I may not complete, works as an AND gate and its inputs must be true. Okay. That is, an odd level NAND gate works as an OR gate with its inputs complemented. An even level NAND gate works like an AND gate with its inputs true. Okay. Now, this in fact is the crux of the NAND circuit synthesis. Now, let us work out this particular one. What we have is an OR gate, right, that is SA bar is YC or B bar. Now, just for SA bar we will work out and then see. Okay. We will do this for SA bar alone. What did we see? We want OR function, we just need odd level, which means one gate will do. If you have one gate, one NAND gate, we want the output SA bar, right, which is YC or B bar. What does it say? An odd level NAND gate works as an OR gate with its inputs complemented. So, if you want SA bar as the output, which in fact is this, its inputs must be complemented, which means the input for this is YC bar and the other input B bar you complement, it will be B. So, just one NAND gate is enough to implement this function, that is the output SA bar, which is YC or B bar, okay, YC or B bar. The rule says complement the inputs. So, for YC we complement and get YC bar, for B bar we complement, which means we recomplement B bar and get B. So, this in fact is the output of the NAND gate, which we can include here, that is for SA bar we just need one NAND gate and the inputs to this are YC bar, I will call this YC bar, and the other one as B, fine. Similarly, for RA bar, again it is an OR gate. So, we need just one more NAND gate for RA bar, the two inputs. Now, we say YC or B, these are the two inputs. So, again input must be complemented. So, YC bar, it is same as this, right, this itself is YC bar. So, the same YC bar we can give here too, YC bar, and the other input is this also must be complemented, B, which means B bar. So, we must have B bar here. Where do we have B and B bar? We know that we have got it from here, this element, right. So, B bar we can take from here and B we can take from here. Over. So, YC bar is one of the inputs. Actually, our one input will be YC, we have to complement that, all right. Now, continuing, let us go to the other thing, SB bar. Again we have OR function, but this time with 3 inputs, 3 input OR we need, which means a 3 input NAND gate we need, and that again must be complemented. So, for SB bar we will have a 3 input, the inputs must be complemented, right. So, first one YJ, YJ bar complemented will be YJ, YC bar complemented will be YC, A complemented will be A bar, right. Then RB bar, again a 3 input OR gate, that is a 3 input NAND gate, one gate will do. So, we will use a 3 input NAND gate and generate RB bar. This input the same thing as before, inputs must be complemented. So, instead of YK bar complement and generate YK, then YC bar complement, it is YC, which is the same thing as what we have here, YC. The other input is also must be complemented, A bar you complement, you get A, fine. Where do we have A and A bar? We already have them here, right. A will be taken from here and A bar we have it here, okay. We will run this, this is A bar that is A bar. Okay. So, now look at this, we have yc bar here, we have yc here, and we know that yc is an input of the system, right, like yj and yk. Now that we have done it, we do not need these functions anymore, fine. Yj is one input, yc is one input, yk is the third input, right. Now, from yc you invert and you get yc bar, the yc bar that we need. Suppose you happen to have a 2 input NAND gate, fine, you just short that and there you have from yc you get yc bar, fine. Now, we know how exactly using the 3 inputs the 2 states can be arrived at. What we have here is only for the next state. This whole circuit diagram depicts the next state function. We have not yet worked out the output function, right. That is what we have to do next. The output will also incidentally be derived making use of the 2 state variables A and B, right. We will do that. How is it? We have to in fact refer to the Asm chart. Now, we just say yj, yk, yc are the 3 inputs I said, and then the outputs are h1 and h0. Okay. So, you can see that these are the 3 inputs from the external world, and what we have internally is our digital system or machine or component, whatever you call, and the output will have to be generated, which again will be a function of the state, which means A and B. Let us go to the Asm chart. The chart you can see that the 2 outputs H0 and the other output H1, these are generated respectively in these states. What is it? H0 is generated once in state A and again in state B. Similarly, H1 is generated once in state C and again in state D. In fact, directly we will be able to derive the function of H0 and H1. What is it? If we just take a close look at it without going into much working out the details, we can arrive at what is it? See here, look at state of A is 0 here, A is 0 also here. A, that is I am talking about the state variable A. Okay. Then state variable A is 1 here, A is 1 also here. So, whenever the state variable A is 0, H0 is generated. Whenever the state variable A is 1, H1 is generated, right. This is all right. This is in the case of very simple Asm chart, that means a simple component, but let us work it out in a very formal way. What is it? Let us go to the state assignment map, right. We need to refer to that again. I will just call it as a state assignment map. What was that? We had the corner map with A and B, assuming values 0 and 1, and then let us see the chart again and see that A corresponds to A B being 0, B corresponds to A and B being 0 1, right. Now, that is what it is. A and B both are 0 corresponds to state A. A0 B1 corresponds to state B, and A and B both 1 corresponds to state C, and A1 B0 corresponds to state D. This is our state assignment map which we had done earlier. Now, like whatever we did for SA or A functions, remember similarly SB or B function, that is as far as the input is concerned, right. Similarly, for the output also we have to work out what is it. That is, if we take H0, so we have to generate the H0 map. What is that H0 map? This is an output map. It just says you have to see the Asm chart and work it out. Let us first prepare the chart map for it. H0, let us check the Asm chart. H0 is generated in state A and state B, right. H0 is generated in state A and in state B. So, the H0 map will have the entry corresponding to state A and state B. So, 1 means H0, the particular Boolean function is 1 in state A, which means H0 is generated in state A and again it is generated in B. Now, similarly H1 map, okay, we can have H1 map, again similar, not much of a difficulty. A B assuming value 0 1 and see the Asm chart again. H1 is generated in state C, H1 is generated in state C and again in state D, right. So, the H1 map will show that in state C and D H1 will be generated, good. Now, let us work out the Boolean function of H0, that is encircle this, that gives you the function for H0. According to this, H0 is what? It says whenever A is 0, whenever A is 0, H0 is generated, that is what that encirclement shows. That is whenever A bar is true, that is A is 0, right. Whenever A is 0, that is A complemented, this is generated. And what about H1? H1 is generated whenever A is 1. So, the function of H1 is whenever A is 1, that is A, agreed. Whenever A is 1, H1 is generated. Well, this is what I was telling you earlier, this you can arrive at very simply. Now, H0 is A bar and H1 is A, as simple as that. What happened to our state variable B? It is not figuring in the output. And recall what we were talking about master slave flip flop. We said there is one memory element which will follow the inputs and another memory element will be following the internal state, and that is the one which will generate the output. Now, we find A, the outputs H0 and H1, they depend on the state of A. In other words, let us just mark it on the this one. H0 is A bar, that is the output H0, and H1 is A. Agreed? H1 and H0, agreed. What happened to B? It is internal. Now, we find that the output of this component depends on this element A, depending on this output is generated, and depending on some combination of some state of B and some other combination, A state will also be arrived at. Okay. Now, you can see that this element B in fact is the master part and A just follows B, that is the slave one, okay, fine. B for as a master follows the inputs and internally prepares the states and decides something about the state of A, and depending on state of A the output follows immediately. So, this in fact is the master part and that is the slave part, because the slave follows the master. Okay. Good. As you can see here, A, look at the inputs A, clock is there, and then the state of B alone decides what is the state of A. So, A follows B and B follows the inputs, right. B follows, you can just see B's input, if you take a look, it will be following the inputs, and A just follows B. So, A is the slave and B is the master. So, the master keeps an eye on the inputs, changes its states, and the slave follows the master. Good. It is a very simple output function, but nevertheless, even in the case of complex output functions, this is the way to proceed with. Now, do you recall whatever we did on the ROM based design? Now, what we have here is the hardwired logic design, right, hardwired logic design, or I will just put it as simply hardware design. Now, earlier we did a ROM based design and I said that is a ROM based, and that particular one is the firmware design, right. So, why did we do all these designs? Not really to design the flip flop, just to get an idea of what is a hardware design and what is a firmware design. And now link this up with whatever we had done earlier. We had taken a look at the firmware design of a controller of a processor CPU. Okay. Earlier while discussing the data path control, we did the firmware design. Similarly, there is a way to do the hardware design, but the number of states, inputs and outputs in the controller of a CPU will be too many to discuss. So, we took up this example, and through this example just know the relationship between a hardware design and a firmware design and extend, okay, or extrapolate your idea about a firmware based control and a, which is nothing but a micro programmed controller, and the hardware control. Now, this is hardware because everything is wired. You have the two memory elements, and again these two memory elements, what were they? They were again two NAND gates, remember, they were connected back to back, correct. I was working out like this, that is essentially this will also consist of two NAND gates like this. Similarly, here too there will be two NAND gates. So, now we have that entire this also is B bar. So, the entire thing consists of NAND gates, nothing else. So, it is possible to have any logic system or a digital system designed only with NAND gates, and we have just seen it for this master slave flip flop completely. Okay. Now, you just have to extend for any other system with any number of inputs, outputs and states, fine, good. Now, what is it that we had earlier in the firmware design? Let us take a quick look at the Asm chart and see again, because Asm chart was the starting point for both hardware as well as firmware design. That is, the chart describes the behavior of the system, and the system we see consists of 4 states, in this case A, B, C and D, right, and it in each state it checks for some input and it checks for the output. Okay. Then state by state we saw, that is we saw in state A, and that is a state code for A, it generates, the system generates output H0, and it checks for inputs yj and yc. As long as yj and yc are 0, the next state is A itself. If yj or yc become 1, the next state becomes B. This is what we did for one state, which is A. With A as present state, then two possible next state is A itself or B, and the inputs to be checked is yj and yc, and output to be generated is H0. So, this is for one state. Like this we also do for the other 3 states. So, essentially we had 4 such microwords, right. These 4 microwords we put in a read only memory and got the firmware design. Recall? Now, instead here what we have is a hardwired logic, right. You remember in the read only memory we had 4 words, each for each state, one for A, one for B, one for state C, one for state D, remember. Then we had the decoder, so that is nothing but a simple address decoder, that is the read only memory. I also said it is controller read only memory, and any time only one word is taken, and that consists of 3 fields, that is test field, next state field, we are talking about 2 next states possible, and out field and extra logic, and then here we had 2 memory elements A and B, okay. That 2 state A and B will decide what is the which one of this, right, and input to A and B we were getting it from here, we are having some test logic and so on and so forth, right. Agreed? And if you see the Asm chart, we have just reduced the whole the next state as only 2 next states, that is one we call it as a false next state, the other as a true next state. It is possible that in any practical problem there can be more than 2 next states, but everything can be reduced to always only 2 next states, it is possible, right, that is okay. And maybe I will just work out here, because there is a point I want to make here. We are talking about a true or a false next state, which one of these, one will be true next state, the other will be a false next state. One of these will be selected depending on some test logic, and what exactly is to be tested depends on what you get from that word, and here are the actual inputs, okay. And one of these is passed on, and that is the one which forms this 2 code AB, okay. One of these, it is just 2, right. For AB there will be only 2 bits. So, one of these will be selected because that in fact is a multiplexer, and outputs were generated whatever they are. Now, something can be assumed here, this field can be reduced instead of 2 next states, one call it as a true or false next state, okay. One of these can always be assumed. What is it? That is, we can talk about either a true or false we can have, let us say true, okay. Always have only true next state, and then you assume the other next state, that is assumed next state. What is it? We can always say assumed next state is nothing but the present state plus 1, present state plus 1, okay. That is the assumed next state, in which case we need not have 2 fields, we can just have only one field. So, one of these can be removed. What is it? Suppose take a look at the chart. Okay. Suppose I am assuming this. Now, you can see here A, B, the code is 0 0 0 1. So, assume next state is, here I am assuming the true next state is assumed, which means after A the next state will be A plus 1, which will be 0 1 itself, okay, true next state. So, in which case I have to give only one next state field, which is in this case 0 0 itself. That is, I have to give only the false next state, okay. So, that a simple counter can be made use of here. So, the assumed next state is the present state plus 1, but we have to decide. Now, as you can see the Asm chart, we have assumed for the true next state this particular assumed next state, okay. So, in which case we can reduce this particular one also, that is only what you may call as reducing the size of this micro word. Good. Now, that is in fact the firmware approach, and here we have the hardware approach. Now, as I said earlier, for both Asm chart is the starting point, but here we in the read only memory we have this entire state by state information. This in the present state it says what are the inputs to be tested, what are the possible next states, what are the outputs to be generated. Starting from the same consideration only we have derived the hardware also, is it not the same thing? That is, Asm chart was the starting point for both. Good. Now, instead of this particular read only memory which gives this information as per the Asm chart which we discussed earlier, you pull out this read only memory, put some other code and put it back, then the behavior of this machine changes, right. As long as the memory remains the same, it is going to behave as per that Asm chart whatever we have discussed. Instead, if you put some other code, another one comes. So, we talk about the firmware approach, that is, as long as you have the code it is okay. If you change the code it is going to behave differently. Compare that with the hardware part. If you want to change anything, the entire connections will have to be changed, right. So, that in fact brings about the flexibility. That means, the firmware approach brings in the flexibility, and that in fact this is what we saw as the micro program controlled, right, micro program controller for the processor we saw. Now, it is up to you to compare this with the whatever we had discussed for the processor. In connection with processor we discussed the controller, right. Just only one word I took in that particular one, which was giving the data path control, only one. Now, here we have for the entire flip flop. Good.